Hello, this is a short podcast on how to use the StarDrop software, primarily for doing drug profiles on various drugs. If you recall from the video conference, I started from Mathematica, where I have a piece of code here that takes a data set of drugs. In this case, we're just using aspirin as the example, and exports a comma-separated values file for loading in the StarDrop. So I have data, I'm looking for aspirin. I have my results table here, and what we're looking for here is what's called the SMILES format. That's what StarDrop is going to need. That's a simplified molecular input line entry system. And it's going to come up with that this is SMILES format right there for aspirin, and it's going to come up with a name. And if you notice, I wanted to change that name to uppercase. In my output, I added the title structure and active component to the file. And then when I ran the file, I had it export the file as a CSV file, and I called it in this case just drugs, to my desktop so that I could find it. Now I'm going to go and I'm going to open up StarDrop, make my window a little bit bigger here so you can see a little bit, and I'm going to slide this window open so you can actually see some of the names of the tools. Okay, so I'm going to go up here under Open. I'm going to come down to my desktop. I'm going to find drugs.csv. That was the file that came out of Mathematica, and I'm going to go ahead and open it. Notice there it has aspirin in there with the structure. I'm going to say OK, and now aspirin and the appropriate structure are in StarDrop. So when I want to do things on, I need to make sure I select aspirin. You could have hundreds and hundreds of drugs in here. In this case, I just have the one. One of the first things you want to do here is under StarDrop, all of these are essential properties of drugs. So log S is a solubility. There's a solubility at the physiological pH of, that's what blood is, has a pH of 7.4. Log P is a measure of, it's called the partition coefficient. It's a measure of how well the drug gets through membranes. Log D is a variation of that, so on and so forth. Blood-brain barrier is in here. PGP category, these are all things, molecular weight. Hydrogen bond donors, hydrogen bond acceptors, topological polar surface area, flexibility, rotatable bonds. All these are things that you're going to have to know about a drug compound in this course. So I'm just going to select them all, come down here to the bottom, and I'm going to hit the Run button. And what you should see popped up now across the screen are all these properties. Okay. I can also click on this icon here, and I will get a different display. But basically, it's the same information. Okay, so there's all that information there. Okay, so that's what you want to do in here. Okay, under scoring, that's the next tab over. You can make up your own rules here for how you want to evaluate a drug, so you can add a rule, but we're just going to use the ones that are already built in. So this profile here does a profile of how well the drug performs everywhere but in the central nervous system, and taking the drug orally. And then obviously, how does the drug behave in the central nervous system? Lipinski rule of 5, as we mentioned in the video conference, hydrogen bond acceptors, hydrogen bond donors, molecular weight, and log P. There's 4 things here, but it's called the rule of 5 because all of these are multiples of 5. Likewise, non-central nervous system profile and central nervous system profile for when you do the drug intravenously. So I'm going to click on the Lipinski rule of 5, make sure my molecule is selected, hit the Run button. It gives me some warnings. I can ignore those. And I get a Lipinski score of 1. That means this particular drug meets all of these criteria. It has a hydrogen bond acceptors less than 10, hydrogen bond donors less than or equal to 5, molecular weight less than 500, and a log P less than or equal to 5. Because this is aspirin, I probably care about how it does as a central nervous system drug. There's all the categories, by the way, and you can adjust those as you see fit. Notice that the solubility function is of higher importance. Okay, so likewise, I'm going to go down here and I'm going to run that model, and I get a profile there of about 0.354, about 35%. So this is not a great drug for oral central nervous system. I can do, let's try what does non-CNS look like. Okay, significantly higher. I can look at how this fares as an intravenous drug, obviously better. And once again, so I can come up with all of these scores here, and again display them in various ways. Okay, we'll not worry about design at this point. Oh, but it does show you your results there. That's also also a nice little table there. Visualization, we only have one drug here, so it's not much to do here. We could come up with different charts and graphs, and we'll do that later on. Okay, the other thing that you might want to try is what's called the cytochrome P450 engine. This is where it's measuring metabolism. So all of these things here are specific kinds of enzymes that will metabolize drugs. So you have CYP3A4, CYP2D6, CYP2C9. So these are all enzymes in your body that will metabolize these things. You do need to make sure the server is working. So, and I sent you how to do that in a separate email. So server status, I don't have any molecules in the space. I'm going to go ahead and run the server. And what this now tells me is, looking at each of these carbons here, it tells me how well and how much they're metabolized. So looks like my biggest metabolic process is on this particular carbon, just one carbon over from this oxygen bridge here. You'll learn more about this when we do organic chemistry and when we get to the metabolism unit. So for this particular enzyme, for CYP3A4, it's showing me where my metabolism is happening there. Not much happening on the carboxylic, actually nothing happening on the carboxylic acid. If I try a different enzyme, I get some different numbers. Still a pretty high metabolic activity there on that particular carbon. Likewise, if I look at, so what you should be seeing so far for aspirin is I'm getting pretty similar activity in the metabolic processes. That carbon seems to be a real target for metabolic activity. Looks like I didn't get anything here for C28, C2C19, 2E1, or 1A2, and that's okay. All right. We won't be using Torch for a little while, and we will be using Nova possibly as a way to, so this is our what they call our lead drug, and what we want to do is use Nova to generate some other possible drug compounds that may be of interest here. I'm just going to add a bunch of stuff. Actually, let me take a couple of them off, just so we don't have too much stuff. So you can choose a bunch of stuff here. You can look at some particular libraries, and I can hit the run button there. And you can see that I came up, starting with this as the parent compound. Okay, I'm coming up with, it generated this particular structure here. Notice I have an extra, looks like I have an extra carbon here. So it's coming up with all kinds of different ideas of different compounds that I can build based on aspirin as the parent compound. So this is how you could use StarDrop. Again, I would say the primary thing that you can use it for is, these are really all of the, or a lot of the ADMET properties: absorption, distribution, metabolism, excretion options. You can do some scoring profiles here to look at some how these things score for various categories. And again, you could build your own profile, and you will probably have a chance to do that in the course. If you have more than one drug, you can do some visualization work. You can look at some metabolic activity. We'll do Torch later when we get into protein ligand binding. We can look at starting from a lead drug here. Oh, it also put a chlorine on there, looks like. So we can do some comparative studies between the parent compound and some structure that's generated computationally. Okay, I hope this helps, and we'll see you online.